Stephen Hawking stood before a room of physicists in 1976 and told them something that should have been impossible. Black holes destroy information, not by hiding it or scrambling it, but by erasing it from existence entirely. The room did not take this quietly. What Hawking proposed violated one of the deepest principles in physics, a principle so fundamental that questioning it felt like questioning mathematics itself. If he was right, something had to give, and either quantum mechanics was wrong or our understanding of gravity was incomplete, or both turned out to be true. For nearly 50 years, this problem has haunted theoretical physics, driving some of the most brilliant minds of our time to propose ideas that sound like science fiction. Our three-dimensional universe might actually be a projection from a two-dimensional surface. Information about everything falling into a black hole might sit encoded on its boundary like data on a hard drive. The interior of a black hole might not even exist in the way we imagine. This is the black hole information paradox, sitting at the exact point where our two most successful theories of physics collide and refuse to agree. By the end of this video, you will understand what information means in physics and why its preservation matters so deeply. You will learn how Hawking's discovery of black hole radiation created a crisis shaping theoretical physics for half a century. You will see how the holographic principle suggests space itself might work in ways our intuition never anticipated. And you will discover how, just a few years ago, physicists made a breakthrough that many believe finally resolves the paradox, at least in certain theoretical settings. If you find this kind of deep exploration valuable, consider subscribing and leaving a like, as it helps bring more content like this to curious minds everywhere. Now, let us begin. Understanding why information loss poses such a problem requires knowing what physicists mean by information in the first place. Physicists are not talking about human-readable messages or data on a hard drive when they discuss information. They mean something more fundamental: the complete quantum state of a system, all the correlations and relationships allowing you, in principle, to predict how that system will behave and to reconstruct its past. Picture a glass of water where you know the exact quantum state of every particle. You would have all the information about that system, and you could, in principle, run the equations backward to figure out where each water molecule came from, what container held it before, even what cloud it fell from as rain. Quantum mechanics is reversible in this sense, and given complete information about the present, you can reconstruct the past. Physicists call this property unitarity, and it sits built into the mathematical structure of quantum mechanics at its deepest level. Unitary time development means information is conserved, and while it can be scrambled, spread out, or made practically impossible to recover, it is never truly destroyed. The quantum state at any moment contains everything needed in principle to reconstruct any earlier moment. This is not just a philosophical preference, but a mathematical necessity. Unitarity connects to conservation of probability, to the consistency of quantum predictions, to the entire framework making quantum mechanics the most precisely tested theory in scientific history. If unitarity fails, the mathematical foundations of quantum theory start cracking. Hawking was not suggesting a minor modification when he proposed that black holes destroy information. He was suggesting that one of the most fundamental principles underlying all of quantum mechanics might be violated when gravity becomes strong enough. Understanding the paradox requires understanding what a black hole actually is. Einstein formulated general relativity in 1915, replacing Newton's force-based description of gravity with something far stranger: space-time geometry. Matter and energy curve the fabric of space-time, and objects move along the straightest possible paths through that curved geometry. What we experience as gravitational attraction is really the consequence of moving through curved space-time. Carl Schwarzschild found an exact solution to Einstein's equations just 1 year later, in 1916, describing the space-time around a spherically symmetric, non-rotating mass. His solution contained something peculiar: a surface at a specific radius where something dramatic happens to the geometry. This surface carries the name event horizon, and the radius where it occurs is called the Schwarzschild radius, given by the formula R equals 2gm divided by c squared, where g is the gravitational constant, m is the mass, and c is the speed of light. For a black hole carrying the mass of our Sun, the Schwarzschild radius works out to approximately 2.953 kilometers, or about 1.835 miles. A black hole with 10 solar masses would measure roughly 29.53 kilometers, or 18.35 miles, across its horizon. The event horizon acts as a one-way causal boundary. Once something crosses that horizon in classical general relativity, no signal from it can ever reach a distant observer. Light itself cannot escape. The interior of the black hole becomes causally disconnected from the outside universe. This is what makes a black hole a trap. Anything falling in, any matter, any radiation, any information encoded in quantum states crosses a boundary from which there is no classical return. Misconceptions about the event horizon are common, so it deserves careful attention. An event horizon is not a physical surface you can touch or bounce off. It exists as a boundary in space-time, a mathematical surface defined by the property that light rays at that surface, directed outward, do not escape to infinity. The point of no return is defined by causal structure rather than material composition. For an observer falling into a large black hole, crossing the horizon is locally uneventful. Space-time at the horizon is curved, but for a large black hole, that curvature is gentle. Tidal forces, the stretching and squeezing caused by gravity gradients, remain weak, and an astronaut crossing the horizon of a supermassive black hole would notice nothing special at the moment of crossing. This seems to contradict the idea that the horizon is special, that information is encoded there, that the entropy of the black hole is associated with its surface. And here is where it gets interesting. Both descriptions turn out to be valid because different observers describe things differently. A distant observer sees the horizon as active, processing information, eventually releasing it as Hawking radiation, while an infalling observer experiences nothing dramatic at crossing. The apparent tension reflects coordinate dependence of how we describe events near horizons. For decades, the trap seemed absolute. Classical general relativity declared that nothing escapes, and that appeared to end the story. And that changed when Stephen Hawking entered the picture. Hawking published calculations in 1974 and 1975 showing that black holes are not completely black. Treating quantum fields on a curved space-time background revealed something unexpected. Black holes radiate. This is Hawking radiation, and its discovery changed everything. Near the event horizon, quantum effects produce particle pairs, with some particles escaping to infinity while their partners fall into the black hole. The net effect is that the black hole emits radiation and loses mass in doing so. This radiation carries a thermal spectrum, meaning it looks like heat radiation from a warm object. Hawking showed that black holes have a temperature now called the Hawking temperature, determined by a specific formula involving mass. And here is where things get strange. Hawking temperature is inversely proportional to mass, which means bigger black holes are colder, not hotter. This runs opposite to everyday experience, where more stuff usually means more heat. A black hole carrying our sun's mass has a Hawking temperature of approximately 6.17 times 10 to the negative 8 Kelvin, which works out to about 1.11 times 10 to the negative 7 degrees Fahrenheit above absolute zero. For a 10 solar mass black hole, temperature drops to approximately 6.17 times 10 to the negative 9 Kelvin. These temperatures are extraordinarily cold, far below the cosmic microwave background temperature of about 2.7 Kelvin, filling all of space. For astrophysical black holes, Hawking radiation is negligible because they absorb far more energy from their environment than they emit. In principle, if a black hole were isolated long enough, it would slowly radiate away all its mass and eventually disappear entirely. The thermal nature of Hawking radiation sits central to understanding why the paradox exists in the first place. Thermal radiation carries a very specific statistical character. A thermal distribution describes radiation in equilibrium with a heat source at fixed temperature, the kind of radiation you get from hot metal, from the filament of a light bulb, from any object glowing because of its temperature. Thermal radiation is maximally random in a precise sense. Given only the temperature, you can predict average energy at each frequency, but you cannot predict correlations between different emissions. Each photon is statistically independent of every other photon, and the radiation carries no memory of how the heat source was prepared. Hawking's calculation showed exactly this for black holes. The radiation has precisely the statistical properties of thermal emission at Hawking temperature. Measuring it, you would find no evidence of what fell in, and a black hole formed from a collapsed star would emit identical radiation to one formed from a collapsed cloud of hydrogen, distinguishable only by their masses. But here is the subtlety. Hawking's calculation is a leading order approximation, computing the dominant contribution to radiation while missing subleading corrections. These corrections are tiny at any given moment, but they accumulate over the entire evaporation process. The evaporation timescale reveals why this problem remains purely theoretical for now. Time for a black hole to completely evaporate, assuming no matter falls in, scales as mass cubed. For a black hole with one solar mass, evaporation time is approximately 2.10 times 10 to the 67 years. For 10 solar masses, it climbs to approximately 2.10 times 10 to the 70 years. To put that in perspective, the current age of the observable universe is roughly 1.4 times 10 to the 10 years. A solar mass black hole would take more than 10 to the 56 times the current age of the universe to evaporate. and we will never observe this process directly for any astrophysical black hole. Physics does not care about human timescales. What matters is whether the process is consistent with fundamental principles. Hawking argued in 1976 that radiation produced by black hole evaporation is genuinely thermal, carrying no information about what fell into the black hole. A black hole formed from stellar collapse would emit the same radiation as one formed from a giant ball of ice cream. The radiation depends only on mass, charge, and spin, not on specific quantum states of what went in. If true, when the black hole finally evaporates completely, all information about what fell in is gone. Not hidden, not scrambled, but genuinely erased from the universe. This violates unitarity. The final state, thermal radiation, cannot be traced back to the initial state because many different initial states would all produce the same featureless thermal radiation. The connection between past and future is severed and information is destroyed. I remember the first time I truly understood what this meant. Hearing that information might be lost is one thing. Realizing that if Hawking was right, the entire framework of quantum mechanics, the most successful theory in physics, would be fundamentally incomplete, that hits differently. Bekenstein's original insight about black hole entropy deserves attention because it challenged fundamental assumptions about how physics works. Before Bekenstein, the second law of thermodynamics seemed to face a problem with black holes. The second law says entropy never decreases in a closed system. But what happens when you throw something with high entropy, like a hot gas, into a black hole? The gas disappears behind the horizon, and its entropy seems to vanish from the accessible universe. If black holes had no entropy of their own, you could violate the second law by dumping high entropy matter into black holes. The universe would seem to lose track of entropy, and the fundamental law of thermodynamics would fail. Bekenstein proposed in 1972 and 1973 that black holes do have entropy, and this entropy increases when matter falls in. Total entropy of the universe, including the black hole's contribution, never decreases, and the second law is saved. But here is the thing. His formula was strange. Entropy is proportional to horizon area, measured in Planck units, with each Planck area on the horizon contributing roughly 1 bit of entropy. For a solar mass black hole, this works out to an enormous number, approximately 10 to the 77 bits. At the time, this was controversial. If black holes have entropy, they should have temperature, but classically, black holes emit nothing, so they should have 0 temperature. Bekenstein's proposal seemed internally inconsistent. Hawking set out to disprove Bekenstein and instead confirmed him. The radiation Hawking discovered gives black holes exactly the temperature Bekenstein's formula implies, and the pieces fit together beautifully. A new branch of physics, black hole thermodynamics, was born. Entropy scaling with area rather than volume was deeply counterintuitive. In ordinary thermodynamics, entropy scales with volume because a box twice as large holds twice as many particles in twice as many configurations. Entropy counts microscopic arrangements compatible with a given macroscopic state, and more volume means more room for arrangements. Bekenstein argued that black holes work differently, with maximum entropy set by horizon area rather than interior volume. Hawking's discovery that black holes have temperature let him derive a precise formula for this entropy. The Bekenstein-Hawking entropy is given by S equals K sub B times C cubed times A divided by 4G times H bar, where A is horizon area, G is the gravitational constant, H bar is the reduced Planck constant, C is the speed of light, and K sub B is Boltzmann's constant. For a solar mass black hole, this works out to approximately 1.05 times 10 to the 77 times Boltzmann's constant. Converting to bits, information capacity is roughly 1.51 times 10 to the 77 bits. Think about that number for a moment. A single solar mass black hole holds an information capacity exceeding 10 to the 77 bits. For comparison, all digital data ever created by humanity is estimated at roughly 10 to the 22 bits. A modest black hole has an information budget dwarfing anything humans have ever conceived of storing. For a 10 solar mass black hole, capacity climbs to approximately 1.51 times 10 to the 79 bits because entropy scales with horizon area, which scales as mass squared for Schwarzschild black holes. This area scaling of entropy would turn out to be one of the most important clues to resolving the paradox. Bekenstein-Hawking entropy counts something, but what exactly? In ordinary thermodynamics, entropy counts microstates. A gas at given temperature and pressure could be realized by many different arrangements of its molecules, with each arrangement being a microstate. Entropy measures how many microstates are compatible with the macroscopic properties you observe. For black holes, microstates must be quantum gravitational in nature. They are not different arrangements of particles inside the black hole, but different quantum states of space-time geometry itself, or of whatever replaces space-time at the Planck scale. String theory physicists have constructed explicit models where black hole microstates can be counted. For certain special black holes, called extremal black holes, the counting works precisely. You identify the microstates, count them, and the number matches the Bekenstein-Hawking formula exactly. This provides strong evidence that entropy is real, that black holes genuinely have microstates accounting for their thermodynamic properties. Extending this to realistic astrophysical black holes is more difficult because the extremal black holes used in string theory calculations are idealized and do not match black holes we observe in nature. Whatever they are, microstates live at the horizon. This connects to the holographic principle. Information content of the black hole is encoded on its boundary, not distributed through its volume. Each Planck-sized patch of horizon contributes roughly 1 bit of entropy, suggesting fundamental degrees of freedom are associated with the horizon surface. Area scaling of black hole entropy raises a question cutting deep into physics foundations. Why should information scale with area rather than volume? In ordinary systems, entropy scales with volume because degrees of freedom distribute throughout the system. A gas fills its container, atoms are everywhere, and more volume means more atoms, more possible arrangements, more entropy. Black holes work differently, with all entropy associated with the horizon surface. Doubling the radius quadruples the area and roughly quadruples the entropy. Volume increases by a factor of 8, but entropy only increases by a factor of 4. One way to understand area scaling of entropy is through the Bekenstein bound. Gravity limits how much energy, and by extension how much entropy, can be packed into a region. Trying to exceed the limit causes the region to collapse into a black hole. Maximum entropy for any region is set by its boundary area, not its volume. Another way to understand it is through holography. If the boundary can fully describe the interior, then fundamental degrees of freedom live on the boundary. Volume is derived, not fundamental. Number of degrees of freedom scales with area because that is where the degrees of freedom actually are. A third perspective comes from considering how information falls into a black hole. From a distant observer's view, infalling matter never actually crosses the horizon. It slows down and spreads across the surface, heating up and scrambling. Information accumulates on the horizon rather than passing through it into the interior. All three perspectives point to the same conclusion. The horizon is special, and the interior may not be as independent as classical intuition suggests. Area scaling of entropy is a clue that space-time works differently from everyday expectations. Black holes connect to the Planck scale in several ways. The Bekenstein-Hawking entropy formula contains Planck's constant and the gravitational constant combined in ways suggesting microscopic degrees of freedom responsible for black hole entropy are quantum gravitational in nature. Individual bits counted by the entropy formula correspond to quantum gravitational microstates, not classical configurations. The paradox arises because Hawking's calculation uses semi-classical gravity, treating quantum fields on a fixed classical space-time background. This approximation is expected to break down when quantum gravitational effects become important. Resolution to the paradox likely involves physics at or near the Planck scale, physics that semi-classical methods cannot capture. Island calculations reproducing the Page curve are thought to capture some of these quantum gravitational effects, even though they use semi-classical methods in clever ways. They show that naive semi-classical calculation misses important contributions, and including those contributions restores unitarity. Area scaling of black hole entropy suggested something radical about the nature of space itself. Gerard 't Hooft proposed what would become known as dimensional reduction in quantum gravity in 1993. His idea was startling. Information content of a region of space might not scale with its volume, as common sense suggests, but with the area of its boundary. Leonard Susskind developed this further in 1994 and 1995, formulating what is now called the Holographic Principle. This principle suggests that a complete description of physics in a volume of space can be encoded by degrees of freedom living on the boundary of that region. Think of it like a hologram. A hologram is a two-dimensional surface encoding a three-dimensional image. Looking at a hologram, you see depth and perspective, but all information is actually stored on a flat surface. The holographic principle suggests the universe itself might work this way, that what appears to be three-dimensional space might be fully described by information on a two-dimensional boundary. This does not mean we are literally living in a hologram or that reality is an illusion. It means physics of a region might have an equivalent description in terms of degrees of freedom on its boundary, and that description might actually be more fundamental. An analogy helps here. Black hole information capacity scales like area of a boundary, more like pixels on a screen than air molecules filling a room. If maximum information in a region is set by its surface area, then in some sense the surface tells you everything there is to know about the interior. This shift in thinking from volume to surface, from interior to boundary, would prove essential to making progress on the information paradox. The ADS/CFT correspondence deserves deeper exploration because it transformed how physicists approach the information paradox. Anti-de Sitter space is a space-time with constant negative curvature. Unlike our universe, which has a positive cosmological constant and expands forever, anti-de Sitter space curves back on itself at large distances. It has a boundary at spatial infinity, a surface where the geometry reaches a specific structure. Maldaceno's insight was that gravitational physics in this bulk spacetime is exactly equivalent to a quantum field theory living on the boundary. The boundary theory is a conformal field theory, a special type of quantum field theory with enhanced symmetry. It has no gravity at all. The word exactly is crucial. This is not an approximation. Every calculation in the bulk gravitational theory has a precise translation to a calculation in the boundary theory and vice versa. They are two descriptions of the same physics. In the boundary theory, there is no information paradox. The theory is unitary by construction. Quantum field theories satisfy unitarity as a fundamental axiom. Information cannot be lost in the boundary description. If bulk and boundary descriptions are equivalent, then information cannot be lost in the bulk either. Black holes in the bulk might scramble information and make it difficult to recover, but they cannot destroy it. The boundary description ensures unitarity. This does not tell you how information escapes in the bulk language. It does not identify the mechanism or compute corrections to Hawking's calculation, but it tells you the answer must be unitary. The bulk description, properly computed, must preserve information because the equivalent boundary description does. This shifted the conversation from whether information is preserved to how information is preserved. Most physicists, after ADS/CFT, accepted unitarity is maintained. The challenge became explaining the mechanism in gravitational terms. Juan Maldacena took the holographic principle from intriguing idea to something approaching concrete framework in 1997. Maldacena proposed a specific duality between two seemingly different theories. On one side sits a gravitational theory in a d plus one-dimensional space with a particular geometry called anti-de Sitter space, often abbreviated ADS. On the other side sits a conformal field theory, a specific type of quantum field theory without gravity, living in d dimensions. This is the ADS/CFT correspondence, and it changed how physicists think about quantum gravity. The correspondence says these two theories are exactly equivalent. Every process in the gravitational theory has a corresponding process in the boundary theory, and every calculation you can do on one side has a translation to the other side. Here is why this matters for the information paradox. The boundary theory, the conformal field theory, is a standard quantum theory. It is unitary, information is conserved, and there is no information paradox in the boundary description. But the boundary theory is supposed to be exactly equivalent to the bulk gravitational theory, including all black hole physics. If the boundary description is unitary, the bulk description must be unitary too. Black holes in ADS/CFT do not destroy information because the equivalent boundary process does not destroy information. This does not directly solve the paradox in our universe, which is not anti-de Sitter space, but it provides strong evidence that black hole evaporation can be consistent with unitarity in at least some theories of quantum gravity. the apparent conflict between Hawking's calculation and quantum mechanics can be resolved, even if details of how it works in our universe remain unclear. A DS/CFT became a guiding framework, shaping how physicists approach the information paradox, showing that unitarity and gravity can coexist, and providing tools for studying black holes where calculations could be done precisely. If black hole evaporation is unitary, what should we expect to see? Don Page worked out the expected behavior of entanglement entropy during black hole evaporation in 1993, assuming unitarity is preserved. The result is called the Page curve, and understanding it is essential to following recent breakthroughs. Imagine a black hole forming and then slowly evaporating through Hawking radiation. At first, the black hole is large and radiation is sparse. Emitted particles become entangled with the black hole, with each Hawking particle having a partner that falls back in, and correlations between them create entanglement. In early stages of evaporation, entanglement entropy of the radiation grows. More and more radiation is emitted, all correlated with the shrinking black hole, and entropy of the radiation increases as it accumulates. And here is the key insight. If the process is unitary, this growth cannot continue forever. Eventually, entanglement entropy must turn around and start decreasing. As the black hole shrinks further, information must begin returning to the radiation. Late-time Hawking particles must be correlated not just with the black hole, but with early-time radiation, and these subtle correlations encode information about what fell in. The Page curve is the expected shape of entropy as a function of time. It rises at first, reaches a maximum roughly when the black hole has lost half its entropy, then falls, eventually returning to zero when the black hole is gone and all information has been transferred to the radiation. The first time you see the Page curve idea, it reshapes how you think about the paradox. Information return is not instantaneous, not like a safe opening and releasing its contents all at once. It is a slow pivot in entanglement over an enormous timescale, encoded in correlations so subtle they would be essentially impossible to measure. For decades, the Page curve remained a prediction, something unitarity required, but that no one could derive from first principles in a gravitational calculation. Hawking's original calculation gave the wrong answer, predicting entropy keeps rising throughout evaporation, never turning over, implying information loss. The challenge was finding where this calculation goes wrong and computing the correct answer. Something remarkable happened in 2019. Jeffrey Pennington and, independently, Ahmed Almhiri with collaborators showed how to derive the Page curve using gravitational path integral methods. Their approach involved including contributions from what they called islands, regions of spacetime that initially seem to be inside the black hole, but that contribute to entanglement entropy of the radiation. Technical details involve replica wormholes and entanglement wedge computations, concepts from quantum gravity connecting different copies of spacetime in the calculation. The key result is that including these contributions correctly makes entropy of the radiation follow the Page curve. It rises, reaches a maximum, then decreases, just as unitarity demands. This was the 2019 shift, changing how many physicists talk about the paradox. After decades of debate, explicit calculations began reproducing the page curve in controlled settings, and the information paradox, at least in these theoretical models, appeared to have a resolution. The work was done primarily in the context of ADS/CFT and simplified two-dimensional gravity models where calculations are tractable. These are not realistic four-dimensional black holes in our universe, but results strongly suggest principles extend more broadly, that a complete theory of quantum gravity will preserve unitarity and information is not lost. This is the part that still amazes me. For nearly 50 years, some of the smartest people in physics wrestled with this problem, and many thought it might never be solved or would require revolutionary new physics. Using clever mathematical techniques and insights from holography, explicit calculations emerged, giving the right answer. Stephen Hawking's own views on the information paradox shifted over time, and tracking these shifts illuminates the debate. When Hawking first proposed that black holes destroy information in 1976, he seemed to genuinely believe this was the correct conclusion. His calculation showed thermal radiation with no memory of what fell in, and he accepted the implication: unitarity fails in black hole evaporation. This put him at odds with most of the quantum gravity community. Physicists who thought deeply about quantum mechanics found it hard to accept that unitarity could be violated. The mathematical structure of quantum theory seemed to demand information conservation, and giving it up would require rebuilding quantum mechanics from the ground up. Through the 1980s and 1990s, Hawking defended his position. He bet with other physicists about whether information escapes and argued that quantum gravity might genuinely work differently from ordinary quantum mechanics, that the semi-classical calculation captured essential physics. A DS/CFT development in 1997 changed the landscape. Here was a concrete example where gravitational physics was exactly equivalent to a unitary boundary theory. If the equivalence held, black holes in ADS could not destroy information. Hawking's position became harder to maintain. At a conference in Dublin in 2004, Hawking publicly conceded the bet he had made about information loss. He accepted that information is preserved, though he proposed a specific mechanism involving path integrals that not everyone found convincing. By the end of his life, Hawking had joined the consensus that information escapes. His original calculation was not wrong within its approximations. It was incomplete. Semi-classical methods missed quantum gravitational effects that, properly included, restore unitarity. Hawking's shift from skeptic to believer mirrors the broader shift in physics. The paradox he created became the tool establishing information preservation as a guiding principle. The island prescription emerging in 2019 is worth explaining in more detail because it represents a genuine breakthrough in how we compute entropy in gravitational systems. In quantum mechanics, entropy of a region measures how entangled that region is with everything outside it. If you have a region of radiation far from a black hole, its entropy tells you how correlated it is with the rest of the system. Normally, you would compute this entropy by looking only at the radiation region itself, but the island prescription says that in gravitational systems, you should include additional regions, called islands, that might be located elsewhere, even inside the black hole. The prescription works by extremizing a quantity called generalized entropy, which includes both ordinary entropy of matter and a contribution from area of certain surfaces. Finding the configuration giving minimum generalized entropy tells you the true entropy of the radiation. At early times during black hole evaporation, the minimum configuration has no island, and entropy of radiation increases as expected following Hawking's calculation. But at late times, something changes. A new configuration becomes dominant, one where an island inside the black hole is included in the entropy calculation. This island contribution causes entropy to decrease following the Page curve. Transition between these configurations, from no island to island, occurs roughly at Page time, when the black hole has lost about half its entropy. After this transition, information begins returning to the radiation, encoded in correlations the island prescription captures. This might sound like a mathematical trick, but it carries deep physical meaning. The island represents a region that has become entangled with radiation in such a way that it should be considered part of the radiation's quantum state. The gravitational path integral, computed correctly, includes these contributions automatically. Calculations deriving the Page curve use a technique called the replica trick, and in gravitational theories, this leads to something called replica wormholes. Computing entropy in quantum systems is tricky because entropy is not a linear function of quantum state. You cannot measure it directly. Instead, physicists use a trick, compute a quantity called Renyi entropy for integer values of a parameter n, then analytically continue to n equals 1 to get ordinary entropy. For integer n, Renyi entropy can be computed by taking n copies or replicas of the system and connecting them in a specific way. You compute a partition function on this connected system and extract entropy from it. In gravitational systems, replicas are copies of spacetime. When you connect them according to the replica prescription, the gravitational path integral allows them to be joined by wormholes, geometric connections between the replicas. These replica wormholes change the calculation in crucial ways. Without them, you get Hawking's answer. Entropy rises forever. Information is lost. With them, you get the Page curve. Entropy rises, peaks, falls, and information is preserved. Replica wormholes are not physical wormholes you could travel through. They are mathematical contributions to a path integral, configurations that must be summed over when computing quantum gravitational quantities. Their inclusion is dictated by rules of quantum gravity, not by intuition about what should or should not be allowed. This is one reason the 2019 results were surprising. Calculations followed standard rules of quantum gravity, but gave an answer different from what earlier methods produced. Replica wormholes were always there in some sense. It just took clever analysis to recognize their importance and include them correctly. The 2019 calculations introduced a concept called the entanglement wedge that helps explain how islands work. In ADS/CFT, a region on the boundary is associated with a region in the bulk called its entanglement wedge. This is the part of the bulk that the boundary region can reconstruct. Having complete information about the boundary region lets you, in principle, determine everything about its entanglement wedge. For a black hole, entanglement wedge of the boundary starts out including the entire exterior. As the black hole evaporates and more radiation is emitted, the situation changes. At late times, part of the interior, the island, becomes included in entanglement wedge of the radiation. This means radiation, even though far from the black hole, can reconstruct information about a region inside the horizon. Information is not localized at the horizon or in radiation itself, but encoded in correlations between them, and the entanglement wedge tells you what those correlations allow you to reconstruct. The island is the region inside the black hole that becomes part of the radiation's entanglement wedge at late times. Its inclusion causes entropy to turn over and follow the page curve. This might seem like mathematical abstraction, but it carries physical content. It says relationship between interior and exterior is more intimate than classical intuition suggests. Parts of the interior can become associated with the exterior in a precise quantum sense. Information seeming trapped inside is actually encoded outside. The entanglement wedge prescription was developed before island calculations in the context of understanding holographic reconstruction. The 2019 insight was applying this prescription to the black hole evaporation problem and discovering that it naturally reproduces the page curve. Understanding that information is preserved differs from understanding how it is encoded. If information is not destroyed, where does it go and how is it stored in the radiation? The answer, as best we understand it, is that information is not carried in individual Hawking quanta like messages in bottles. It sits encoded in subtle, long-range correlations across the entire radiation field. Each individual Hawking particle looks thermal, essentially random. Examining any single photon or particle emitted from an evaporating black hole, you find nothing special, just thermal radiation at Hawking temperature. Information is not readable in any individual piece, but correlations between particles, the way their quantum states are entangled with each other, encode everything that fell in. These correlations build up over the entire evaporation process, which for a solar mass black hole takes 10 to the 67 years. Information is shredded into correlations, distributed across an astronomical number of particles, spread over unimaginable timescales. This is why information recovery is not practical, even if it is in principle possible. Recovering information about what fell into a black hole would require collecting every single Hawking particle emitted over the entire evaporation, and then performing measurements, detecting correlations between them. For any realistic black hole, this is impossible, not just with current technology, but with any conceivable technology. The information paradox is not about whether we can read what fell into a black hole. It is about whether laws of physics are self-consistent, whether the universe keeps its books balanced, whether fundamental equations preserve the connection between past and future, even when we have no practical way to verify it. The distinction between information in physics and information in everyday life is worth emphasizing again, because confusion on this point leads to misunderstanding. When you hear that a black hole stores 10 to the 77 bits of information, imagining files on a hard drive, books in a library, or photographs in an album, is natural. This intuition is misleading. Bits counted by black hole entropy are not data in any human-readable sense. In physics, information refers to quantum state of a system. It includes all correlations and entanglement relationships determining how the system will behave. A system's information content is the minimum number of bits needed to specify its quantum state completely. For a black hole, this information is stored in quantum gravitational microstates. We do not fully understand what these microstates are. They are not classical configurations, not arrangements of particles inside the black hole. They are quantum states of geometry itself, or of more fundamental degrees of freedom we have not yet identified. When matter falls into a black hole, its quantum state is absorbed. The black hole's quantum state changes to incorporate this new information. Total information content of the system, matter plus black hole, is conserved. But information is now encoded in the black hole's microstates rather than in original matter. When the black hole evaporates, this information is transferred to radiation, not as readable data, but as correlations between Hawking particles. Quantum state of radiation eventually contains all information that was in original matter, encoded in entanglement relationships spanning astronomical scales and timescales. This is information preservation in the physics sense. The mathematical structure connecting past to future remains intact. Quantum state at late times determines quantum state at early times. No actual book can be recovered, but the underlying physical principle is upheld. The phrase quantum state deserves unpacking because it appears throughout discussions of the information paradox and carries specific technical meaning. In quantum mechanics, systems are described not by definite positions and velocities, as in classical physics, but by quantum states. A quantum state encodes all information about a system that quantum mechanics allows you to know. It determines the probabilities of different measurement outcomes and how the system will interact with other systems. Quantum states are strange objects. They can be superpositions, combinations of different classical possibilities existing simultaneously until measured. They can be entangled, meaning the state of one particle is correlated with the state of another, regardless of the distance between them. When physicists say that information is preserved in black hole evaporation, they mean that the quantum state of the radiation at late times encodes the quantum state of whatever fell in. The encoding is extremely complex, spread across correlations between particles emitted at different times, but it is complete. Given the late-time quantum state of all the radiation, you could in principle determine the early-time quantum state of everything that fell in. This is what unitarity guarantees. The quantum state at any time determines the quantum state at any other time, forward or backward. The laws of quantum mechanics are reversible. Information encoded in quantum states is conserved. The Hawking calculation seemed to show that black holes violate this principle, producing radiation whose quantum state at late times does not encode the quantum state of what fell in. The Page curve and island calculations show this is wrong. Properly computed, the late-time radiation does encode the early-time infalling matter. Unitarity holds. This matters because quantum mechanics is not just a theory of subatomic particles. It underlies chemistry, materials science, electronics, and increasingly, technology. If quantum mechanics were fundamentally incomplete, if unitarity failed in some circumstances, we would need to revise our understanding of these fields. The resolution of the information paradox tells us that quantum mechanics is more robust than the paradox suggested, that unitarity survives even the extreme environment of black hole evaporation. The word scrambling appears frequently in discussions of the information paradox, and understanding what it means helps clarify why information recovery is so difficult. When you drop a sugar cube into hot tea and stir, Sugar dissolves and spreads throughout the liquid. Molecules that made up the cube are still there, but they are distributed uniformly, mixed into the tea. In principle, knowing position and velocity of every molecule, you could figure out where sugar started. In practice, this is impossible. Information is preserved but scrambled. Black holes are the most efficient scramblers in physics. When matter falls into a black hole, its quantum state gets scrambled across the horizon in what physicists call the fast scrambling time. This scrambling spreads correlations throughout the system, distributing information across all degrees of freedom of the black hole. After scrambling, information about what fell in is not localized anywhere. It sits encoded in correlations between parts of the system in entanglement patterns spanning the entire horizon. Extracting original information would require measuring all of these correlations simultaneously. This scrambling is why individual Hawking particles carry no readable information. Each particle looks thermal, random, precisely because it is entangled with the rest of the system in a maximally scrambled way. Information is there, but distributed so thoroughly that no local measurement can access it. One of the strangest ideas to emerge from the information paradox involves how different observers describe the same events. Susskind and collaborators developed the concept of black hole complementarity, suggesting that observers at different locations might give very different accounts of what happens to matter falling into a black hole, and both accounts might be valid within their respective domains. A distant observer describes infalling matter as approaching the horizon and heating up, spreading across the horizon, getting scrambled into high-temperature degrees of freedom, eventually coming back out as Hawking radiation. Information never actually crosses the horizon from this viewpoint. It is processed at the horizon and returned. The infalling observer experiences something completely different. Crossing the horizon is locally uneventful. Space-time near the horizon of a large black hole is only mildly curved, and an infalling observer would notice nothing special at the moment of crossing. They pass through and continue falling toward the singularity. The complementarity idea suggests something fascinating about how physics describes extreme situations. Think of it as two ledgers, two different accounting systems tracking the same events in different ways. A distant observer watching matter fall toward a black hole describes what happens using exterior coordinates. In this description, infalling matter never actually crosses the horizon. It slows down, redshifts, and appears to hover just above the horizon, its clock running slower and slower relative to distant time. Matter heats up, gets scrambled across the horizon, and eventually comes back out as Hawking radiation. The ledger balances. Information in equals information out. An infalling observer, falling along with the matter, describes events using freely falling coordinates. In this description, the horizon is crossed without drama. Space-time at the horizon of a large black hole is only mildly curved, and nothing special happens at the moment of crossing. The observer continues falling toward whatever lies at the center. The ledger records a one-way trip into the interior. Both descriptions are valid within their domains. The distant observer never sees information enter and fail to return. The infalling observer never sees information stopped at the horizon. No single observer encounters a contradiction. This does not mean both descriptions are simultaneously true in some naive sense. It means the question of what really happens depends on who is asking and what they can measure. Horizons are strange boundaries where different descriptions apply to different observers. This perspective shift, from expecting one true description to accepting multiple complementary descriptions, reflects how quantum mechanics and general relativity force us to think differently about fundamental questions. Unitarity deserves more careful explanation because it sits at the heart of the paradox. In quantum mechanics, state of a system is described by a mathematical object called a wave function, or more generally, a state vector. As time passes, this state changes according to the Schrödinger equation. The Schrödinger equation is linear, and its solutions preserve a property called the norm of the state. Preserving the norm is equivalent to preserving probability. Total probability of finding the system in some state must always equal 1. If the norm changed, probabilities would not add up correctly, and the theory would become inconsistent. The mathematical way to express this is that time development is unitary. A unitary transformation preserves norms and inner products. It can scramble information arbitrarily, spreading correlations across the system, but it cannot destroy them. Unitarity means quantum state at any time contains complete information about state at any other time. Run equations forward and you predict the future. Run them backward and you reconstruct the past. No information is ever lost. If black hole evaporation violates unitarity, implications are severe. Different initial states could lead to the same final state, and you could not reconstruct past from present. The deterministic character of quantum mechanics would fail, and the mathematical structure making the theory work would break down. This is why physicists were so reluctant to accept information loss. Unitarity is not a peripheral feature of quantum mechanics, but central to the theory's consistency. Giving it up would not be a small modification, but would require rebuilding quantum mechanics from scratch. Before the 2019 breakthrough, the information paradox took several dramatic turns, including a proposal that the event horizon might be replaced by a firewall of high-energy radiation. In 2012, Almheiri, Marolf, Polchinski, and Sully published a paper arguing that the seemingly smooth horizon described by general relativity might actually be a violent place. Their argument became known as the AMPS firewall paradox, and it shook the field. The argument went roughly like this: if information is preserved, then late-time Hawking radiation must be entangled with early-time Hawking radiation, as the page curve requires. But semiclassical reasoning suggests that each Hawking particle should also be entangled with a partner that fell into the black hole. Quantum mechanics limits how many things can be maximally entangled at once. Something has to give. AMPS argued that what gives is smoothness of the horizon. Instead of a locally uneventful boundary that infalling observers pass through without noticing, there might be a firewall, a surface of extremely high energy destroying anything trying to cross. This was disturbing because smoothness of the horizon was one of the most robust predictions of general relativity. An infalling observer should notice nothing special at the horizon of a large black hole, and the firewall would contradict this basic expectation. The firewall debate raged for years, with different physicists proposing different resolutions. The 2019 island calculations do not directly resolve the firewall debate, but they suggest information can escape without requiring a firewall. The entanglement structure is more subtle than simple arguments assumed. The information paradox exists because it sits at the boundary between two theories, and understanding that boundary requires knowing something about scales involved. The Planck scale marks the energy or length where quantum effects and gravitational effects become comparably important. At this scale, our current theories break down, and we need a complete theory of quantum gravity that we do not yet have. The Planck length is approximately 1.616255 times 10 to the negative 35 meters, working out to about 5.302 times 10 to the negative 35 feet. The Planck time is approximately 5.391247 times 10 to the negative 44 seconds. These numbers are incomprehensibly small. The Planck length is about 10 to the 20 times smaller than a proton. No experiment has ever probed anywhere close to this scale, and no conceivable experiment in the foreseeable future will do so. The semiclassical approximation Hawking used deserves more explanation, because understanding its limitations is key to understanding the paradox. In a full theory of quantum gravity, both matter and space-time would be treated quantum mechanically. We do not have such a theory yet. General relativity describes space-time classically as smooth, curved geometry. Quantum mechanics describes matter as wave functions and operators. Combining them remains the great unsolved problem of theoretical physics. The semi-classical approximation is a compromise. It treats space-time classically as a fixed background geometry and treats matter quantum mechanically as quantum fields propagating on that background. This approximation is valid when gravity is weak and space-time curvature is gentle. It breaks down when gravitational effects become comparable to quantum effects at the Planck scale. Hawking's calculation uses this approximation. He took the Schwarzschild black hole geometry, treated it as a fixed classical background, and computed how quantum fields behave on that background. The result was Hawking radiation with a thermal spectrum. The approximation is valid at any given moment during evaporation. The black hole is large, curvature at the horizon is gentle, and quantum gravitational corrections are small. But the approximation is applied over the entire evaporation, taking 10 to the 67 years. Small errors accumulate over this time. Island calculations show that these accumulated errors are crucial. Quantum gravitational effects negligible at any instant add up to change the final answer completely. The semi-classical calculation gets the page curve wrong, not because it is bad physics, but because it misses contributions that become important over long times. This is a general lesson about approximations. An approximation can be excellent for local physics and still miss global features. Hawking's calculation is correct locally, but incomplete globally. The information paradox connects smallest and largest scales in physics, and stepping back to see this connection reveals something about the nature of physical inquiry. At one extreme sits the Planck scale. The Planck length, approximately 1.616 times 10 to the negative 35 meters, is so small it dwarfs any scale humans have ever probed experimentally. The Planck time, approximately 5.391 times 10 to the negative 44 seconds, is so short no measurement could ever resolve it. At the other extreme sit astrophysical black holes. Stellar mass black holes span kilometers. Supermassive black holes at galactic centers span distances larger than our solar system. These are among the largest discrete objects in the universe. The information paradox connects these scales. Entropy of a black hole involves horizon area measured in Planck units. Microstates counted by that entropy are quantum gravitational, involving physics at the Planck scale. But the objects themselves are astronomical, visible through gravitational wave detectors and X-ray telescopes. This connection is not coincidental. Black holes are laboratories for quantum gravity precisely because they bring together extreme gravity and extreme quantum effects. The paradox arises because quantum mechanics and general relativity must both be relevant, and resolution requires understanding how they fit together. Human inquiry has pushed from both ends. We study largest structures in the universe and probe smallest scales accessible to our experiments. The information paradox sits where these efforts meet, where physics of the very large and physics of the very small collide. We have made remarkable progress understanding this collision. We do not have a complete theory of quantum gravity, but we have learned principles that any such theory must satisfy. Information must be preserved. Holography must play a role. The page curve must be respected. These constraints, derived from studying the paradox, guide the search for deeper understanding. The fact that humans can even recognize the information paradox is itself remarkable. We are creatures who developed on a planet's surface, navigating at human scales with senses designed for survival. Nothing in our immediate experience requires knowledge of quantum field theory or the Planck scale. We could live perfectly well without knowing gravity exists in the way we understand it now, without wondering why unitarity should be preserved. Yet here we are, measuring forces at microscopic scales, colliding particles at unprecedented energies, asking whether reality contains information that must be conserved even when it falls into a black hole. The gap between the world we directly experience and the world we have learned to probe is vast. This capability reflects something special about human cognition: the ability to reason abstractly, to build instruments extending our senses, to construct mathematical frameworks describing aspects of reality we can never directly perceive. The information paradox is not something anyone could notice by casual observation. It emerges from careful theoretical analysis of relationships between fundamental theories. Holographic thinking goes further. It requires imagining physics encoded on boundaries, relationships between bulk and surface that our brains did not develop to picture. The fact that physicists can formulate these ideas, derive their consequences, and design frameworks to test them is a testament to the power of mathematical reasoning. None of this guarantees we will find all answers. Reality is not obligated to be comprehensible at every level we seek to understand it. Some questions might not have solutions in terms humans can grasp, or solutions might exist but lie forever beyond verification. What we can say is that the attempt to understand is worthwhile. Even questions that remain partly unsolved generate insights, motivate new frameworks, and deepen appreciation of how strange the universe might be. The 2019 results represent major progress, but the information paradox is not completely solved. Several important questions remain open. First, Island calculations work best in controlled theoretical settings, particularly anti-de Sitter space and simplified two-dimensional gravity models. Extending these results to realistic four-dimensional black holes in a universe with positive cosmological constant like ours remains an active research area. Second, calculations show information is preserved and derive the page curve, but they do not provide a detailed operational picture of how information is encoded in radiation. We know the answer is right, but the mechanism remains somewhat opaque. Third, questions about the black hole interior remain contentious. What happens to an observer who falls in? How do we describe the interior consistently with the exterior description? Fourth, the relationship between holography and emergence of space-time is still being understood. If the boundary theory fully describes the bulk, in what sense does the bulk exist independently? The information paradox has driven theoretical physics for 50 years and continues to do so. Each resolution opens new questions, each answer reveals new puzzles. Pause and appreciate how strange the holographic principle really is. In everyday experience, storage scales with volume. A bigger hard drive holds more data, a larger room holds more air molecules, and a bigger box has more possible arrangements of its contents. Volume determines capacity. Black holes violate this intuition completely. Their information capacity scales with surface area, not volume. Consider what this means. If you have a spherical region of space, maximum information it can contain is determined by area of its boundary, not by how much space is inside. Doubling the radius increases volume by a factor of 8, but only increases area by a factor of 4. This is like saying contents of a warehouse are determined not by interior volume, but by pixels on its walls. If you treat the horizon's entropy as an information budget, even a modest mass black hole implies information capacity vastly beyond human-scale storage. The files are quantum microstates, not classical disks, living on the boundary rather than filling the volume. You might wonder why physics should care about boundaries at all. The answer connects to deep features of gravitational theories. In ordinary quantum field theory, number of degrees of freedom in a region scales with its volume. More space means more room for excitations, more places where particles can be. This is the intuitive expectation. Bigger regions contain more stuff. In gravitational theories, this expectation fails. Gravity is attractive and universal. Trying to pack too much energy into a region causes gravity to collapse it. There is a maximum amount of stuff you can fit into a given volume before it becomes a black hole. This maximum is set by the Bekenstein bound. Maximum entropy in a region is proportional to its boundary area, not its volume. Gravity prevents exceeding this bound by collapsing overstuffed regions into black holes. Bekenstein-Hawking entropy of a black hole saturates this bound. A black hole is the most entropic object that can fit inside a given boundary, holding maximum information content allowed by gravity. This suggests the boundary is more fundamental than the volume. True degrees of freedom might live on the boundary, and the volume might be a derived concept. Holography makes this precise. Boundary theory captures everything, and the bulk emerges from it. From this perspective, it is not surprising that black hole information is encoded on the horizon. The horizon is the boundary of the black hole, and boundaries are where fundamental degrees of freedom live. Information falling into the black hole is absorbed by the horizon and eventually released through Hawking radiation. The mystery is not that information ends up on the boundary. The mystery is how our experience of a three-dimensional world emerges from boundary physics. How does the interior appear to exist? How do observers inside describe their experience? These questions remain at the frontier of research. An important caveat runs through all of this. Strongest results come from idealized models, not realistic astrophysical black holes. Island calculations reproducing the page curve work best in controlled theoretical settings. Most explicit computations use anti-de Sitter space, a spacetime with negative cosmological constant curving in on itself at large distances. Our universe has a positive cosmological constant and expands outward. Anti-de Sitter space is not our universe. Many computations also use simplified two-dimensional gravity models where calculations are more tractable. In 2 dimensions, much of the complexity of 4-dimensional gravity is absent, and certain features can be studied in isolation. These models capture important physics, but are not complete descriptions of real black holes. This does not mean results are irrelevant. Principles derived from controlled models are expected to extend to more realistic settings. The page curve should describe any unitary evaporation process. The holographic principle should apply broadly. The island prescription should generalize. But demonstrating these extensions explicitly is challenging. 4-dimensional gravity with positive cosmological constant is harder to work with than its 2-dimensional or anti-de Sitter cousins. Tools making simpler cases tractable do not always carry over. This is why the information paradox remains an active area despite 2019 progress. Physicists want to extend results to realistic 4-dimensional black holes, understand mechanism in detail, and connect abstract mathematics to concrete physical processes. The broad outline is established, but filling in details continues. Model dependence is a feature of theoretical physics at the frontier. We study idealized situations not because they describe reality exactly, but because they illuminate principles that should apply more generally. The information paradox is no exception. Treating the horizon's entropy as an information budget, black holes become the universe's most capacious libraries. A solar mass black hole holds approximately 1.51 times 10 to the 77 bits of information. To put that in perspective, all digital data ever created by humanity, every photograph, every video, every document, every website, every database amounts to roughly 10 to the 22 bits. A single, modest black hole has information capacity 10 to the 55 times larger than everything humans have ever stored. A 10 solar mass black hole is even more extreme, holding approximately 1.51 times 10 to the 79 bits. But calling this a library is misleading. The files are not classical data that can be read sequentially. They are quantum gravitational microstates, degrees of freedom we do not fully understand, living on the horizon in ways defying classical visualization. The horizon is not a surface in the ordinary sense. It is a null surface, a boundary in space-time where light rays can neither escape nor fall further in if directed outward. Degrees of freedom associated with the horizon are not made of atoms or bits in any familiar sense. They are quantum gravitational, related to structure of space-time itself at scales near the Planck length. When Bekenstein proposed that black holes have entropy, He was suggesting this entropy counts something, that microstates underlie the macroscopic black hole, and counting them gives the Bekenstein-Hawking formula. But what exactly is being counted remains somewhat mysterious even today. In string theory and related approaches, physicists have constructed models where microstates can be identified and counted, and the counting gives the right answer. Whether this description applies to realistic astrophysical black holes is still being studied. The library exists, its capacity is astronomical, but we do not yet fully understand the books it contains. Consider the Schwarzschild radius, which sets the scale of the event horizon. For one solar mass, this is approximately 2.953 kilometers or 1.835 miles. You could walk across the event horizon of a solar mass black hole in about half an hour, if walking were possible there. For 10 solar masses, the radius grows to approximately 29.53 kilometers or 18.35 miles. A supermassive black hole at a galactic center can have a radius larger than the orbit of Neptune. The temperature numbers are equally striking. A solar mass black hole has temperature of approximately 6.17 times 10 to the negative 8 Kelvin, about 60 billionths of a degree above absolute zero. This is far colder than anything humans have ever created in a laboratory, far colder than the cosmic microwave background, far colder than anything in the observable universe. A 10 solar mass black hole is 10 times colder still, approximately 6.17 times 10 to the negative 9 Kelvin. The entropy numbers are astronomical in the literal sense. A solar mass black hole holds approximately 1.05 times 10 to the 77 times Boltzmann's constant in entropy, translating to approximately 1.51 times 10 to the 77 bits of information. For comparison, a human body contains roughly 10 to the 27th atoms. A solar mass black hole has information capacity roughly 10 to the 50 times larger than the number of atoms in a human body. The evaporation time dwarfs any timescale humans can comprehend. At 2.10 times 10 to the 67 years for a solar mass black hole, you would need to write a number with 67 digits just to express how many years are involved. The age of the universe has only 10 digits. These numbers illustrate why the information paradox is about principle, not practice. No measurement will ever verify that information escapes. The question is whether laws of physics are self-consistent, whether mathematics works, whether quantum mechanics and gravity can coexist without contradiction. Every number we have discussed deserves to sit with you for a moment. Black holes with horizons spanning kilometers. Temperatures measured in billionths of a degree above absolute zero. Information capacities exceeding 10 to the 77 bits. Evaporation times stretching to 10 to the 67 years. Durations so vast they make the age of the universe seem instantaneous. These are not abstract numbers. They describe real objects, real processes, real features of the universe we inhabit. Black holes exist. They have temperature. They carry entropy. They will eventually evaporate, even if that evaporation takes longer than any meaningful timescale. The question of what happens to information during that evaporation connects these astronomical facts to the deepest questions in physics. It connects the largest objects we know to the smallest scales physics can describe. It connects the curvature of space-time to the quantum correlations between particles. Resolving this connection required new ideas: holography, the page curve, islands, replica wormholes. Each idea built on previous work. Each breakthrough required decades of preparation. The 2019 calculations did not emerge from nothing. They emerged from 50 years of sustained effort. This is what theoretical physics looks like when it works. Not sudden inspiration, but accumulated understanding. Not individual genius, but collective effort. Not final answers, but progressively better questions. Numbers involved in black hole physics are so extreme they deserve explicit attention. A solar mass black hole has a horizon about 3 kilometers across, a distance you could drive in a few minutes. Surface area, set in information capacity, is about 110 square kilometers. On that surface, the black hole stores approximately 1.51 times 10 to the 77 bits of information. Writing that number out with no scientific notation, you would write a 1 followed by 77 zeros. The piece of paper you would need does not exist. The black hole evaporates over 2.10 times 10 to the 67 years. The universe is about 1.4 times 10 to the 10 years old. Evaporation time is more than 10 to the 57 times longer than current age of the universe. Hawking temperature is about 6 times 10 to the -8 Kelvin. The coldest laboratory temperatures humans have achieved are around 10 to the -10 Kelvin. A solar mass black hole is about 600 times colder than the coldest thing humans have ever made. Now picture information escaping. Each Hawking particle carries essentially no readable information. Information sits encoded in correlations between particles emitted at vastly different times, particles traveling in opposite directions for billions of years. Recovering information would require collecting every particle and measuring correlations spanning the entire radiation field. Consider a thought experiment illustrating the stakes of the information paradox. Imagine writing a book, a unique manuscript existing nowhere else, recording every word, every page, every detail in a quantum state that could, in principle, be reconstructed. Now drop the book into a black hole. In the semiclassical picture, the book crosses the horizon, falls toward the singularity, and is destroyed. The black hole eventually evaporates, emitting thermal radiation carrying no trace of the book's contents. The manuscript is gone forever, not just physically destroyed, but erased from the universe's quantum ledger. In the unitary picture, something different happens. The book crosses the horizon and is scrambled into the black hole's degrees of freedom. As the black hole evaporates, quantum state of the book is gradually transferred to radiation, encoded in correlations between particles. After 10 to the 67 years, when the black hole is gone, complete quantum state of the book exists in the radiation field, in principle recoverable. Neither scenario allows you to actually read the book again. In the semiclassical picture, the book is destroyed. In the unitary picture, the book's state is scrambled across an astronomical number of particles spread over unimaginable distances and times. Practical recovery is impossible either way. But the difference matters fundamentally. In the unitary picture, laws of physics remain consistent. The universe maintains a complete record of everything that happens, even if that record is inaccessible. In the semi-classical picture, information is genuinely lost, and the connection between past and future is broken. Resolution of the paradox says the book survives, not as a readable manuscript, but as correlations in the radiation preserved by mathematical structure of quantum mechanics, encoded in ways defying any practical attempt at recovery, but that keep the universe's books balanced. The distinction between information in physics and information in everyday life matters because confusion on this point leads to misunderstanding the paradox itself. Physicists are not claiming that you could, even in principle with unlimited technology, actually read the message that fell into the black hole. The information is scrambled beyond any possibility of practical recovery. What they are claiming is that the mathematical structure of physics remains consistent, that the equations connecting past to future continue to work, that unitarity holds. This is a subtle distinction, but an important one. The paradox is not about whether black holes are good places to store secrets. They are excellent at that job. The paradox is about whether the laws of physics are internally consistent, whether quantum mechanics and general relativity can both be correct, whether the mathematical frameworks we use to describe reality fit together without contradiction. The answer, as best we can tell from the 2019 calculations and the holographic framework, is yes. The frameworks fit together. Unitarity holds, information escapes, encoded in correlations that no observer could ever hope to measure, but that nonetheless preserve the mathematical consistency of physics. This might seem like a purely theoretical concern, but theoretical consistency matters. A theory that contradicts itself cannot be correct. Finding where our theories contradict and resolving those contradictions is how physics advances. The information paradox was a contradiction, or at least appeared to be one, and its resolution teaches us something about how quantum mechanics and gravity work together. Take a moment to think about what we have covered. A black hole forms, perhaps from the collapse of a massive star. It has temperature inversely proportional to its mass, so the more massive it is, the colder it becomes. It has entropy proportional to its horizon area, an information capacity dwarfing anything humans have ever conceived of storing. The black hole radiates slowly over timescales vastly longer than current age of the universe. Watching this process from far away, you would see thermal radiation, featureless and random. But buried in that radiation, encoded in correlations between particles separated by unimaginable spans of time, is everything that ever fell in. Quantum state of every atom, every photon, every particle that crossed the horizon is preserved in subtle patterns of the radiation. Try to picture that. Not information stored in one place, readable and accessible, but information shredded across an astronomical number of particles, spread over 10 to the 67 years, encoded in correlations that no measurement could ever practically detect. This is what unitarity demands. This is what the page curve describes. This is what island calculations confirm. The trap is real. Once you cross the event horizon, there is no return, no signal you can send to the outside, no way to communicate with distant observers. The black hole swallows everything that enters, but information is not trapped. It leaks out, particle by particle, correlation by correlation, over time scales, making the age of the universe look like an eye blink. The black hole is a trap, but the information escapes. If unitarity is preserved and information escapes, where did Hawking's original calculation go wrong? This is one of the most important questions in the field, and the answer reveals something deep about how semi-classical approximations break down. Hawking's calculation uses quantum field theory on a fixed, curved space-time background. Space-time is treated classically as smooth, curved geometry. Quantum fields, the matter and radiation, are treated quantum mechanically, but space-time itself is not. This is the semi-classical approximation. Within this approximation, Hawking computed radiation emitted by a black hole. He found it was thermal, with precise temperature determined by the black hole's surface gravity. The calculation was correct within its assumptions. The problem is that those assumptions miss something crucial. The semi-classical approximation treats black hole geometry as fixed and eternal. It does not fully account for back reaction of radiation on geometry. More importantly, it does not include quantum gravitational effects becoming important over long timescales. Island calculations show that including certain quantum gravitational contributions, specifically island regions and replica wormholes in the gravitational path integral, changes the answer. These contributions are small at early times but become dominant at late times, causing entropy to turn over and follow the Page curve. In essence, Hawking's calculation is correct at early times, but misses physics becoming important at late times. Corrections needed to restore unitarity are extremely subtle, encoded in small deviations from thermality that build up over the entire evaporation process. This is why the paradox was so difficult to resolve. Corrections to Hawking's answer are tiny at any given moment, but they accumulate over 10 to the 67 years to produce an entirely different final state. Finding these corrections required new tools and insights that took decades to develop. Information preservation does not mean practical information recovery, and this point is worth emphasizing. Even if the paradox is fully resolved and unitarity is preserved, you will never recover a message thrown into a black hole. The barriers are not technological, but fundamental. First, there is the timescale problem. A solar mass black hole evaporates over 10 to the 67 years. You would need to collect Hawking radiation for this entire period. Current age of the universe is roughly 10 to the 10th years. Even starting to collect now, you would need to continue for a duration, making the history of the universe look instantaneous. Second, there is the collection problem. Hawking radiation is emitted isotropically in all directions. Particles spread outward at the speed of light. Collecting all of them would require detectors surrounding the black hole, extending outward over astronomical distances, covering the entire sky from the black hole's perspective, operating perfectly for 10 to the 67 years. Third, there is the measurement problem. Information sits encoded in correlations between particles, not in individual particles. Extracting information requires measuring quantum correlations between particles emitted at vastly different times, particles that have traveled in opposite directions for billions of years. The measurement apparatus required defies imagination. Fourth, there is the practicality of quantum mechanics itself. Even with all particles and all correlations, reconstructing the original state would require quantum computations of a scale dwarfing anything conceivable. Information is preserved in principle. The mathematics says it survives. But preservation does not mean accessibility. The universe keeps its records in a form that no observer could ever read. The inverse relationship between black hole mass and temperature deserves attention because it is deeply counterintuitive. In everyday experience, bigger things can hold more heat. A large pot of water takes longer to cool than a small one. More stuff generally means more thermal energy. Black holes work backward. The more massive a black hole is, the lower its temperature. The coldest black holes are the largest ones, and the hottest black holes are the smallest ones. This happens because Hawking temperature depends on surface gravity at the horizon, which decreases as the black hole gets larger. A more massive black hole has a gentler horizon, a larger radius where space-time curves less sharply, and this gentler curvature produces less energetic Hawking radiation, resulting in lower temperature. As a black hole evaporates and loses mass, it gets hotter. A solar mass black hole has temperature of about 6 times 10 to the -8 Kelvin. If it could evaporate down to a millionth of a solar mass, it would be 1,000,000 times hotter. In final moments before a black hole disappears completely, it becomes extraordinarily hot and bright. Temperature also explains why astrophysical black holes are effectively eternal. The cosmic microwave background filling all of space has temperature of about 2.7 Kelvin. Any black hole larger than about the mass of the Moon has temperature lower than this, absorbing more energy from background than it emits, gaining mass rather than losing it. Only in a much colder future universe could they begin to evaporate. For evaporation to begin, the universe would need to cool below Hawking temperature of these black holes. The CMB temperature decreases as the universe expands, and eventually, in the far future, the CMB will cool enough that even supermassive black holes will begin to evaporate. This will take an incomprehensibly long time. Long after the last stars have died, long after all ordinary matter has decayed or fallen into black holes, long after the universe has become cold and dark, black holes will finally begin their slow fade. One of the most profound implications of the information paradox and its resolution is what it suggests about the nature of space itself. In classical physics, space is the stage on which physics happens. Particles move through space, fields propagate through space, and space itself is a fixed background that everything else is embedded in. This view is deeply intuitive. It matches our everyday experience of moving through a three-dimensional world. The holographic principle challenges this view fundamentally. If physics in a volume can be completely described by degrees of freedom on its boundary, then in what sense is the volume independent? If a two-dimensional theory captures everything about three-dimensional physics, what does the third dimension mean? These questions do not have definitive answers yet, but they point toward a radical possibility. Space might not be fundamental. It might emerge from something deeper, something that does not involve spatial extension at all. In this picture, the boundary theory is more fundamental than the bulk. The three-dimensional interior is a useful description, valid in certain regimes, but it emerges from boundary degrees of freedom rather than existing independently. Space is not the stage. Space is part of the show, emerging from more basic quantum information. The information paradox supports this view in a specific way. Resolution involves information on the boundary being connected to the bulk interior in intricate ways. Islands inside black holes become part of entanglement wedge of the exterior radiation. Sharp distinction between inside and outside, between interior and boundary dissolves. If space is emergent, then questions we ask about black hole interiors might be misguided. The interior might not have an independent existence that can be described separately from the exterior. What happens inside might be encoded in the same degrees of freedom as what happens outside, just described from a different perspective. This is speculative, but it shows how deep the information paradox goes. Resolving it requires rethinking not just black holes, but the nature of space and time themselves. The information paradox and its resolution through holography carry profound implications for how physicists think about space itself. If the boundary of a region can fully encode everything in its interior, then in what sense is the interior independent? If a two-dimensional theory can describe three-dimensional physics, what does that say about reality of the third dimension? These questions touch on the nature of space-time and whether it is fundamental or emergent. In conventional thinking, space is the arena in which physics happens. Particles move through space, fields propagate through space, and space itself has a fixed structure that physics takes place within. Holographic thinking suggests something different. Space might not be fundamental, but might emerge from more basic degrees of freedom living on a boundary. The three-dimensional description we use might be a convenient approximation, valid in certain regimes, but not the deepest level of description. This is speculative, but it is where the physics points. A ds/CFT is an exact duality, meaning the boundary theory is not an approximation, but an equivalent description. If true, bulk spacetime is not more fundamental than the boundary. They are two ways of describing the same physics. What this means for our universe, which is not anti-de Sitter space, remains unclear. The cosmological constant in our universe is positive, not negative, and space-time geometry is different. But the information paradox has pushed physicists to think about space in new ways. Resolution of the paradox involves physics at the boundary, affecting physics in the interior. Emergence of interior from boundary degrees of freedom is central to understanding how information escapes. Space, in this picture, is not a fixed stage, but a dynamic structure intimately connected to quantum information. You might wonder why physicists care so deeply about what happens to information in a process taking 10 to the 67 years that can never be observed directly. The answer is that the information paradox tests consistency of our most fundamental theories at their intersection. General relativity and quantum mechanics are both extraordinarily successful. General relativity describes gravity with precision, allowing us to detect gravitational waves from merging black holes billions of light-years away. Quantum mechanics underlies all of chemistry, all of electronics, all technology, defining modern life. But these theories do not fit together seamlessly. At the Planck scale, where both effects become important, we do not have a consistent framework. We need a theory of quantum gravity, and we do not have one yet. The information paradox is a pressure test. It takes the two theories to a regime where both are relevant and demands they give consistent answers. If they cannot, something must change. For decades, the paradox suggested our understanding was incomplete. Either quantum mechanics needed modification to allow information loss, or general relativity's picture of black holes needed revision, or something entirely new was required. Resolution emerging from holography and island calculations suggests quantum mechanics survives intact. unitarity is preserved. The picture of black holes needing modification is the semiclassical one, the approximation treating quantum fields on a fixed classical background. Quantum gravity effects, even when small, change the answer in crucial ways. This has implications beyond black holes. It tells us something about how quantum gravity works, about relationship between bulk and boundary, about emergence of space-time itself. The information paradox is a window into physics at scales we will never directly probe. Let us take stock of what we have covered. Black holes are regions of space-time where gravity is so strong that nothing, not even light, can escape once it crosses the event horizon. Classical general relativity describes them as perfect traps, one-way doors that matter and radiation can enter but never leave. Hawking radiation changed this picture. Quantum effects cause black holes to emit thermal radiation, slowly losing mass over timescales vastly longer than the age of the universe. For a solar mass black hole, evaporation takes approximately 10 to the 67 years. The information paradox arises because Hawking's calculation produces thermal radiation appearing to carry no information about what fell in. If true, this would violate unitarity, one of the foundational principles of quantum mechanics ensuring information is conserved and the connection between past and future is maintained. Black hole entropy, discovered by Bekenstein and refined by Hawking, scales with horizon area rather than volume. A solar mass black hole has information capacity of approximately 1.51 times 10 to the 77 bits, far beyond anything humans could store. The holographic principle, proposed by T. Hooft and Susskind, suggests information in a region of space is encoded on its boundary. This counterintuitive idea gained concrete support from Maldaceno's ADS/CFT correspondence, providing an exact duality between gravitational physics in a volume and quantum physics on its boundary. The page curve describes expected behavior of entropy during unitary evaporation. Entropy rises at first, reaches a maximum roughly at the halfway point, then decreases as information returns to the radiation through subtle correlations. In 2019, calculations by Pennington, Almhiri, and collaborators showed how to derive the page curve using quantum gravitational methods, including island contributions to entropy. This represents major progress toward resolving the paradox, at least in controlled theoretical settings. The page curve became a benchmark. Any correct theory must reproduce it. Stakes were clear and constraints were tight. Physicists knew what answer they needed to get, but did not know how to derive it from gravitational physics. The 2019 calculations changed that. They showed how to include quantum gravitational contributions that had been missing from Hawking's original calculation. The island prescription and replica wormholes provided the missing pieces. For the first time, gravitational calculations produced the page curve. This did not solve every problem. Questions remain about how to extend results to realistic black holes, about what happens to observers who fall in, about the detailed mechanism by which information gets encoded in radiation. But the main obstacle, the inability to derive the page curve from gravity, was overcome. The trajectory of the information paradox illustrates something about how science works at the frontier. Problems get identified, partial answers accumulate, frameworks develop that constrain what answers are possible. Eventually, If the problem is tractable at all, enough pieces come together that resolution becomes possible. Not every problem in physics works this way. Some problems might be too hard for human minds. Some might require technologies we cannot build. Some might not have answers in terms we would recognize. But the information paradox, despite taking 50 years, shows that sustained effort on well-posed problems can produce results. The paradox Hawking identified in 1976 appears to be resolved, at least in outline. Information escapes black holes, encoded in correlations spanning astronomical timescales, preserved by unitarity even in the most extreme gravitational environments. The black hole is a trap, but information escapes. This understanding comes from bringing together general relativity, quantum mechanics, string theory, holography, and careful mathematical analysis. No single approach would have sufficed. The resolution required synthesizing insights from multiple frameworks, a reminder that nature does not divide neatly into separate domains. The relationship between interior and exterior, between bulk and boundary, between volume and surface, continues to generate new insights and new questions. Every resolution opens new puzzles, and every answer reveals new mysteries. This is not frustrating, but exciting. It means the information paradox, even after 50 years, continues to teach us something new. It means physics at the frontier remains alive, generating questions faster than we can answer them, pointing toward deeper understanding. The next generation of physicists will inherit these questions. They will try to extend the island calculations to realistic black holes, to understand what happens to observers who fall in, to connect the abstract mathematics to observable physics. Some will find answers. Others will find that their questions lead to even deeper questions. This is how understanding grows. Not by completing a picture that stays fixed, but by revealing that every picture is part of a larger one. The information paradox taught us about holography, about the relationship between gravity and quantum mechanics, about the nature of space itself. What it teaches next remains to be seen. For now, the central question appears answered. Information survives black hole evaporation, encoded in radiation spanning astronomical timescales, preserved by unitarity in ways we are still learning to describe precisely. The black hole is a trap for matter, for light, for anything that crosses the horizon. But information escapes. The universe keeps its books balanced, even in the most extreme environments it contains. History of the information paradox illustrates how theoretical physics makes progress on fundamental questions. Hawking identified a problem in 1976. His calculations seemed to show that black holes destroy information, contradicting a basic principle of quantum mechanics. The problem was sharp and clear. Two highly successful theories gave contradictory answers. For decades, physicists debated. Some accepted information loss, some proposed modifications to general relativity, some looked for loopholes in Hawking's calculation, and some developed new theoretical frameworks that might resolve the tension. Holography emerged as a guiding principle. The idea that boundaries encode interiors, that area scaling of entropy suggests dimensional reduction, gained traction. A DS/CFT provided a concrete realization where unitarity was built in. The debate sharpened. Firewalls were proposed and contested. The page curve became a benchmark. Any correct theory must reproduce it. In 2019, explicit calculations derived the page curve from gravitational physics. The island prescription and replica wormholes showed how to include quantum gravitational contributions that Hawking's original calculation missed. The paradox, in controlled theoretical settings, appeared resolved. This is not the end of the story. Extending results to realistic black holes, understanding the mechanism in detail, clarifying what happens to infalling observers, all remain active areas. Progress continues, but the overall trajectory is clear. A paradox was identified. Decades of work developed concepts and tools needed to address it. Breakthroughs came when pieces finally fit together, and now we understand something we did not before. Information survives black hole evaporation. This is how fundamental physics advances, not by sudden revelation, but by sustained effort over decades, building concepts and techniques, testing ideas against constraints until finally the answer emerges. We began with Hawking standing before a room of physicists, telling them that black holes destroy information. 50 years later, the consensus has shifted. Most physicists now believe information is preserved. The page curve, once a theoretical prediction, can now be derived from explicit calculations in certain settings. Holography provides a framework where unitarity is built in, and the information paradox, while not fully solved in all its details, appears to have a resolution. The black hole is still a trap. Once you cross the horizon, there is no return, no signal you can send reaching the outside, no rescue coming for you. The one-way nature of the event horizon remains a feature of classical general relativity and persists in the quantum treatment. But the information is not trapped. It leaks out slowly over timescales dwarfing the age of the universe, encoded in correlations between particles that no observer could ever collect or measure. The mathematics says it survives, and the universe keeps its records. This resolution comes at a conceptual cost. We must accept that space might not be fundamental, that boundaries can encode interiors, that what looks like 3 dimensions might emerge from 2. We must accept that semiclassical approximation, so powerful in most settings, misses crucial physics when applied to the full lifetime of a black hole. When I first learned about the information paradox, it seemed like an abstract puzzle, something only specialists would care about. The more I studied it, the more I realized it sits at the heart of fundamental physics. It tests whether our best theories are consistent with each other, probes the nature of space and time, and asks whether the universe maintains a complete record of everything that happens, or whether some things can be genuinely forgotten. The answer, as best we can tell, is that nothing is forgotten. The universe remembers everything, even if those memories are scattered across radiation fields over billions of years, encoded in correlations too subtle to ever detect. The next time you look up at the night sky, consider what this tells you about the universe. Somewhere out there, black holes sit at centers of galaxies, swallowing matter, growing slowly, radiating imperceptibly. Each one is a library of information, holding quantum states of everything that ever fell in, encoded on horizons far beyond human reach. Somewhere out there, stars are collapsing into black holes, crossing the threshold from which nothing returns, their information preserved in microscopic degrees of freedom we do not fully understand. And somewhere in the mathematics of physics, the equations balance. Unitarity holds. The connection between past and future remains unbroken. We are part of a species that figured this out, part of a tradition of inquiry that asked questions about black holes, about information, about consistency of fundamental theories, and found answers. The answers are not complete, and much remains unknown, but the progress is real. The information paradox reminds us that deepest questions in physics often arise where theories collide, where smooth mathematics of one framework meets precise predictions of another and demands reconciliation. It reminds us that progress sometimes requires decades of sustained effort, false starts, partial answers, and eventual breakthroughs. Thank you for joining me on this exploration of one of the strangest puzzles in physics. If you found value in this, consider subscribing and sharing this video, as it helps bring more deep dives like this one to curious minds everywhere. The black hole is a trap, but the information escapes. Sleep well tonight, knowing that even in the most extreme environments the universe contains, the laws of physics hold together, and nothing is truly lost. Good night.